Alright, so in this video I'm going to be explaining another important article with the title Towards Robust Graph Incremental Learning on Evolving Graphs. This paper in ICML 2023. Incremental learning is a machine learning approach that involves training a model on a sequence of tasks rather than all tasks at once. This ability to learn incrementally from a stream of tasks is crucial for many real-world applications. However, incremental learning is a challenging problem on graph-structured data, as many graph-related problems involve prediction tasks for each individual node, known as node-wise graph incremental learning. This introduces non-independent and non-identically distributed characteristics in the sample data generation process, making it difficult to maintain in the performance of the model as new tasks are added. So we focus on the inductive NGIL problem, which accounts for the evolution of graph structure, structural shift, induced by emerging tasks. We provide a formal formulation and analysis of the problem and propose a novel regularization-based technique called structural shift risk mitigation to mitigate the impact of the structural shift on catastrophic forgetting of the inductive NGIL problem. We show that the structural shift can lead to a shift in the input distribution for the existing tasks and further lead to an increased risk of catastrophic forgetting. So I've explained catastrophic forgetting in my playlist for continual learning. So humans are capable of acquiring new information continuously. This is the motivation of this continual learning and all of these incremental learning. So this is an illustration of the difference between transductive and inductive NGIL. Tau 1 and Tau 2 are two consecutive tasks. In the transductive setting, the one hope ego graph of the vertex with a red circle would remain the same, while in the inductive setting, the graph may change as new tasks are introduced and the overall graph structure evolves. So this is an illustration of the progression of inductive NGIL. Each task I results in an update to the model's parameters. Going from theta 1, theta 2 to theta 3 is an update to model parameters. So, of course, using data from the new task. When a new data comes, for the new task, then we have a different theta 2. And then you see first we have V1, and then we have V2, and then we have growing, it's a graph evolution. And new vertex patches associated with each task are introduced. The graph structure changes, potentially altering the input distribution of existing vertices through changes in their ego graphs. So if you just focus on this node, you see at the next time we have a different we add a different neighbor to that. Also at the next time step, then we have not only this one, but also from different parts of the graph. So you see that this is an evolution of the ego graph of the circled vertex. So this is an illustration of a structural shift risk mitigation. We are sampling, and then we give it to the GNN to have divergence distance. So this is incremental training in development phase. The figure above illustrates what task data the model used for training and evolution. So we assume we have a stream of training tasks, tau 1, tau 2, tau m, and then by observe the vertex batches v1, v2, v sub m that are drawn from an unknown undirected graph. So the observed graph structure at training task is induced by accumulative vertices. To accommodate the nature of node-level learning tasks, in which the information used for inference is aggregated within the k-hop neighborhood of a node, we adopt a local view in the learning problem. So this n sub k is k's neighborhood of vertex v, and in nk of v form an ego network, ego neighborhood of vertex v, which consists of the local node feature matrix and a local adjacency matrix. We use G sub v as a random variable. Of course, we use these ego graphs a lot in a graph explainability. I have a playlist for graph explainability in graph neural network or even graph representation. So we will talk about it there. And then H is the hypothesis space, F is a classifier. F is classifier, H is hypothesis space, and this L is just the loss function. And this is the generalization risk R. R is the generalization risk of the classifier F. So catastrophic forgetting risk is this one, that we call it catastrophic risk of a classifier, because for each classifier F, we have a different risk function. So after being trained on tau, task number m, can be characterized by the retention of performance on previous vertices, which translates to retention of performance of the classifier F from the previous tasks. So structural shift represent our main result on connection between structural shift of the evolving graph structure and the structural and the catastrophic forgetting risk. So to illustrate the phenomenon of structural shift more concretely, we consider graph generation process with two communities, community 1 and community 2. The feature vectors of vertices in community 1 are drawn from a distribution n sub 1, and those of vertices in community 2 are drawn from another distribution n sub 2. And their expectation are not the same. So the connectivity probability for vertices of the same community is denoted as P sub in. And the connectivity probability of vertices of different community is denoted as P sub out. Now, note that the setting above is an instance of the commonly used graph generation model for node classification. Consider an incremental learning setting consisting of 2 training tasks and associated observed vertex batches. We define C sub 1 to be a function that counts the number of vertices in community 1 for a given vertex batch, and function C sub 2 is the same. I mean, they count the number of community 2 for a given vertex. Then they have this proposition that we can have this expectation, which is not equal to each other if they condition on different tasks. And so, you know what is maximum mean discrepancy? So they use this maximum mean discrepancy to use it for this CFR bound. And F is a reproducing kernel Hilbert space with its associated kernel K. And then there is an upper bound on this CFR, which is a structural shift. Then they try to minimize this. Of course, we always include the training loss, the original train, because we have a classifier. And then the next two, they use maximum mean discrepancy to reduce this loss. This is structural shift mitigation. And then they experimented on Quora Full, Reddit, OGB archive. And therefore, evaluation metric, they use APS, average performance sequence, also average forgetting sequence.